Welcome to the deep dive. So if you're involved in AI deployment, maybe development, or even if you're just curious about what comes next after, the big GPU cluster, you know, the quest for efficiency is it's relentless.
It really is. And for decades, computer architects have been looking at the brain for inspiration.
Right. The ultimate parallel low power processor.
Exactly. It's an ambition that, it goes all the way back to people like von Neumann and Turing, but the mission is really changing now. We're moving beyond just inspiration. We are actively trying to uh, replicate the brain's architecture in mass-producible chips.
And that's our focus today. It's strictly technical. We really want to understand the architectural differences, the performance implications, basically the why, the technical why behind all the incredible efficiency claims for neuromorphic computing.
And that why, it really starts with the benchmark that nature has already set for us.
Okay.
Think about something like the brain of a cockatiel parrot. It's tiny, operates on maybe 50 milliwatts of power.
Less than an LED?
Yeah, less than most LEDs. And yet that tiny brain handles complex high-speed flight, navigation, real-time sensing, learned behaviors.
When you look at those kinds of tasks, things that need an immediate, flexible response to the real world, that little biological engine still outperforms our best computer architectures by orders of magnitude in speed, weight, power, everything.
Precisely. So the vision here isn't just to model the brain. It's about understanding the principles of computation at the circuit level, how all the components interact, and then mapping that insight onto silicon. That's where the breakthroughs are.
Okay, so let's get into that. Let's unpack the core biological circuitry, because that's what defines the architecture. We don't need a huge biology lecture, but what are, say, the top 3 architectural principles from that neuron blueprint that we really need to focus on?
Okay, so the first big one is communication. Neurons communicate with these little voltage pulses. We call them spikes. And these spikes travel along the axon, which is like the output wire, to the connections, the synapses. But the really critical part here is how information is encoded.
Ah, the technical secret. It's not about how strong the signal is. It's all about the timing.
That is absolutely vital. In biological systems, spikes are binary events. They have no magnitude. They're either on or off. All the information is encoded entirely by the specific times that they fire. It creates this incredibly dense, time-based code.
Okay, so that's principle 1.
Yeah.
Time-based binary communication. What's the second?
The second is the complexity of the connectivity.
Right.
If you look at the network level, it's just stunning. A single neuron typically connects to, say, 10,000 others. So this system is not built on that simplified, deeply layered feed-forward topology that we see in almost all of today's deep learning models.
10,000 connections per node. That implies just massive parallelism and, I guess, a lot of irregularity.
And that's the third principle, recurrence. These are recurrent and irregular networks. There are loops everywhere. So the computation isn't some step-by-step arithmetic process. It's an emergent result.
Emergent? What do you mean by that?
Think of it like a physical system. Like ripples in a pond, the neurons are constantly storing, releasing, and aggregating energy, and the computation is the emergent result of all those massive ongoing interactions.
So, okay, on one hand, you have this massive, complex, recurrent structure communicating with these time-encoded binary events. That sounds computationally expensive, but the claim is extreme efficiency. How do we resolve that contradiction? Where does the efficiency come from?
This brings us right to the core technical payoff. So let's run our neural signal check. Here's why this development actually matters at a technical level. We can compare 2 ways of solving a common problem, something like visual object recognition.
Perfect. So let's start with the conventional path. A deep neural network, a DNN running on, traditional hardware.
Right. So in a conventional DNN, your input image is a snapshot. It's a huge array of numbers, of pixels. And to do the recognition, you have to perform a massive number of multiply accumulation operations, or MACs.
And you're running those at gigahertz speeds.
Exactly. But we both know the crucial bottleneck isn't the speed of the MACI operation itself, it's moving the data.
It's always data movement.
It's always data movement. All those huge matrices with the learned features, they have to be streamed over and over again from memory across the bus into the computing cores. So that memory interface, it just becomes this huge sequential bottleneck. And this whole brute force approach just costs a ton in raw operations and energy.
Okay, so now let's bring in the alternative, the neuromorphic approach with a spiking neural network, or SNN. How does it tackle the same problem and somehow win on energy, even though its components are, what, operating on a millisecond timescale?
Mhm.
Much slower.
It wins through two things: sparse encoding and asynchronous operation. First, an SNN doesn't process raw pixels.
Hmm.
The input gets converted into spikes right at the sensor level, let's say a digital retina. And these spikes encode features things like texture or motion, not just raw intensity. This pattern of spikes arriving at different times creates what we call a spatiotemporal signature.
So it's like a time-sensitive fingerprint of the input. And instead of moving this giant redundant array of pixel data around, the network is just responding to a sparse, specific temporal signature that already represents high-level features.
Precisely correct. And the spike pattern is distributed across, thousands of parallel neurons. Each of those neurons has learned to recognize a particular temporal signature. So the better the match between the input spikes and a neuron's learned signature, the faster that neuron is going to fire its own spike.
And that must lead directly to the core efficiency mechanism, the way the hardware manages its power.
Crucially, yes. Unlike a conventional clock-driven chip that's always drawing power, a digital SNN only uses power when a neuron actually spikes or processes an incoming spike. It's true asynchronous power management. And on top of that, the decision process itself is self-regulating.
Explain that self-regulation part. Is that the fine-grained power gating idea?
It is. As the feature neurons start matching the input and firing their own output spikes, there's an integrated inhibitory network that's sensing that activity. As soon as enough output spikes are generated to hit a confidence threshold, yep, that's a cat,
Uh-huh.
the inhibitory network broadcasts a stop message to all the associated neurons. And this instantly power gates the remaining activity at a really fine microarchitectural level. The computation just stops the moment the decision is made.
Wow. That is a massive architectural contrast. A conventional system runs the entire matrix multiplication from start to finish, even if the answer was obvious in the first few steps. But an SNN can just stop.
Exactly. So the SNN gets you the same low latency thanks to how fast the signals propagate, but at a huge reduction in raw operations and in energy. The key is that the system only operates when and where information is actually changing.
That makes total sense for efficiency inside the chip. But let me bring up a real challenge that I know deployment professionals are facing right now. If this whole system relies on spikes, how much performance do you lose when you have to interface with conventional non-spiking sensors or traditional cloud data? I mean, is the software stack just too immature to make this worth the pain of integration yet?
But that's the billion-dollar question, isn't it? And you're right, converting existing data streams into spikes, that encoding step, it does add some latency and complexity up front, but the huge energy savings downstream often justify it, especially for anything at the edge. But the real architectural unlock, the big prize, is the shift towards native event-driven systems.
Okay, so let's go there. Let's transition to enterprise deployment. If the fundamental advantage is this sparse, asynchronous, event-driven communication, what specific applications does this unlock for professionals out there designing high-value systems?
It really motivates a complete paradigm shift. Because these systems are so inherently sensitive to tiny changes in temporal correlations, they're brilliant at spotting anomalies really, really quickly.
Can you give us some more tangible examples, something beyond just generalized robotics?
Sure. Think about real-time network anomaly detection. In a conventional system, you have to batch up these large windows of network data to run your analysis. An SNN can process network flows directly as sparse events. A spike could be a connection attempt or a dropped packet.
Okay.
And the system can immediately register a very subtle, time-sensitive deviation from the normal pattern of activity. This could let you do things like sub-millisecond fraud identification or a really rapid cybersecurity threat assessment.
Right, because you're not waking up large parts of the chip to process irrelevant business-as-usual information.
Exactly. Only the specific neuron pathways affected by that change get activated. It dramatically reduces energy and latency compared to, streaming giant matrices around in the cloud.
So this architecture, it's not a program in the traditional sense. It's a nonlinear, event-driven dynamical system. How does that change the fundamental way we think about computation?
Well, when you create these massive recurrent connections, computation stops being about executing instructions and it becomes a search for stability. The input data disrupts the network, and the computation is just the emergent result of the network settling into some new, stable equilibrium state. That state is the result.
So we're not executing A plus B equals C in a sequence. We're sort of poking a physical like system and just watching where it settles.
That's a great analogy. It's like you have a set of interconnected gyroscopes. You push one, the whole system starts oscillating, and eventually it settles into a new, stable configuration. And learning from an AI perspective is also emergent. The network literally self-organizes. It reconfigures its own parameters to find a better adapted state for whatever its objective is.
And that brings us right back to the software maturity issue, doesn't it?
Yeah.
We're so used to things like backpropagation and optimization gradients, which all rely on this continuous synchronous data flow.
Correct. And backpropagation as we know it is extremely difficult, if not impossible, in these sparse asynchronous SNNs because nothing is synchronized. So developers have to rely on very different training methods, things that often mimic biological processes like spike timing dependent plasticity or FTDP. And that's the biggest software hurdle right now, just training these high-dimensional dynamic systems reliably and at scale.
That is a fascinating synthesis of biology and engineering. It feels like we're fundamentally pivoting away from streaming matrices through brute force arithmetic units to propagating sparse, time-encoded spikes through these complex recurrent networks.
It is a profound architectural shift. It's all designed to maximize the sparsity and temporal encoding that's inherent in biological computation. And because the output of these systems is defined by the network settling into a new equilibrium state, this leads to a really critical challenge for anyone who's trying to scale this technology.
Okay, so what's the final question we should be asking ourselves about this new computational paradigm?
The question is this: what analytical tools, what training methodologies must we innovate to effectively guide and, maybe more importantly, ensure the stability of these complex, high-dimensional dynamical systems as they scale up for large-scale enterprise deployment? Because navigating the stability of an emergent, non-linear system, that is a completely different problem than just optimizing a deterministic algorithm.
That's a great note to leave on. We'll dive into the architectural implementation details, so how these concepts actually map into mass-producible chips in the next deep dive.